So we are talking about solving simple trig equations. So we're not going to get too wild and crazy, but we are going to look at some different trig equations that kind of take our knowledge of factoring and things like that, and our knowledge of sine and cosine and tangent and cosecant and secant and cotangent, and they make these big, beautiful equations for us to solve. It's like the best of Algebra 2 and trigonometry all in one problem. It's an exciting, exciting day. So, when we're solving these trig functions, what's going to happen is our x or our theta, a lot of times it'll be a theta since we'll be talking about looking for an angle, we're going to be looking for a missing angle, something inside the sine, something inside the cosine function. So when we're doing that, we want to make sure that the first thing we do is isolate those trig functions. So the first thing you always want to remember to do is isolate the trig function. So we want to make sure that we get the trig function all alone. So that'll be our first goal. Anytime we get these problems, is we want to get rid of any numbers, any coefficients, anything that we can separate out and get away from the trig function, we want to, because we want to just have like sine of x or cosine of x. We want to make it as simple for us to look for the missing angle as possible, so we want that trig function to be all alone. After we isolate the trig function, then we're going to look at the unit circle and pick out the coordinate that has the value we're looking for. So we might be looking for when sine is 1/2. So we're going to go around the unit circle and look for where my sine value is 1/2. So you're going to be looking for coordinates that contain your values. Look for coordinates on the unit circle. And we've seen that the unit circle has a lot of repeating numbers as we travel around. So more likely than not, you're going to have more than one answer. Because if I was looking for where sine is 1/2, I'm looking for any y value that's 1/2. And as I go around, I see that I have two places on my unit circle with a sine of 1/2. So the last thing you always want to do is check for multiple answers. So you just want to make sure that you didn't miss possibly any of those repeating values on the unit circle when you're picking out your answers. So each one of these, before we solve the one that has the trig function in it, we're just going to solve a standard equation, dust off any Algebra 2 skills that we may have forgotten to make sure that we feel okay with it. So if we look at the first one, x plus the square root of 2 equals negative x. All we have to do there in order to solve for x is combine our like terms. All right? Normally, I would add x to both sides, or I could subtract this x. Either way, I'm going to add x. When I do that, I'm going to get 2x plus the square root of 2 equals 0. Then I'm going to subtract the square root of 2, which even though that looks weird, we actually like the square root of 2 now because we know that's one of our numbers in our unit circle that kind of repeats a lot. So even though our numbers might look a little bit strange in these equations, they're doing that on purpose so that it's easy for us to pick out values off the unit circle. So as long as I do the same thing to both sides, I'm okay here. So I get 2x equals negative square root of 2. And then I divide by 2 on both sides. And I get x equals negative root 2 over 2. My x is all by itself, so back in the day I was good to go. That was my answer, right? My square root's in the numerator, so I don't need to rationalize it. Life's good. So we're going to do exactly the same thing when we're solving the sine of x plus square root of 2 equals negative sine of x. The only difference is the last step, we're going to have to look at the unit circle to evaluate when that happens. So the first thing I want to do, I'm going to move over my sign. When I move over my sine of x, I now just have 2 sines of x, because it's basically like sine of x is acting like my variable right now. So I add them together, I get 2. Plus square root of 2 equals, nothing's left over here, so 0. Now I want to subtract my square root of 2, because I know I want to get my sine all by itself. So when I subtract square root of 2, these cancel out. I get 2 sine of x equals negative square root of 2. I divide by 2. And I get sine of x equals negative root 2 over 2. So now I need to ask myself, okay, where does sine actually equal negative root 2 over 2? So this is where I need to pull in my unit circle. So what I'm going to do, I'm going to actually take this and drag it on top here. And we're lovely, not transparent. So I'm going to bring this over, and I want to look for anywhere that sine, so sine's my y value, right? I want to look for anywhere my y value is negative root 2 over 2. So I'm literally just going to travel around my unit circle like this and look for any y value coordinate that's a negative root 2 over 2. I also know if my y values are negative, I can just check the third and fourth quadrant, right, because that's where my y values are negative. So I can look, and I see I have negative root 2 over 2 here, and negative root 2 over 2 here, which means my answers are going to be 5 pi over 4 and 7 pi over 4. So x equals 5 pi over 4 and 7 pi over 4, because at those 2 points I have a y value of negative root 2 over 2. So after I get that trig function all by itself, I just use the unit circle to find the radian values where that statement is true. So far, you're okay? Cool. So now let's look at square root method. If we wanted to solve something like 3 x squared minus 1 equals 0. We know we've got to add 1 first, right? We add 1, we get 3x squared equals 1. Then we divide by 3, divide by 3. We get x squared equals 1 over 3. Then we need to get rid of our square root. So we get x equals, anytime you take a square root, you're going to have the positive and the negative version of the answer. I have positive or negative square root of 1 over 3. I could leave it like that, or if I'm feeling fancy and I want to simplify it, I could say, okay, I have positive or negative square root of 1 over square root of 3, because anytime I have a square root with division, I can break the square root up into both numbers, which is also the same thing as saying positive or negative square root of 1 is just 1. Square root of 3, I don't know. That's not a whole number, so I'm going to leave it as square root of 3. Can I leave a square root in the denominator? No, I've got to rationalize that, right? So I would multiply by square root of 3, both parts. So I really have here x equals positive or negative square root of 3 over 3 would be my final answer. So I'm going to do exactly the same thing with tangent, that 3 tangent squared x minus 1. Do the same steps. I'm just going to then have to evaluate the tangent at the end. So in order for me to solve this, and when I look at this, tangent squared x is the same thing as saying tangent of x all squared. They mean exactly the same thing. They just put the squared next to the tangent so that you know it's 2 tangents, not 2 x's. So that you know that it's not x squared, it's tangent that's being squared. So when they write it, instead of having to use the parentheses just to simplify it a little bit more, they put that squared before the x and after the trig function. Means the same thing. So the first thing we want to do is add the 1, right? We add 1. We get 3 tangent squared x equals 1. We divide by 3. We get tangent squared x equals 1/3. We want to get rid of the squared before we get rid of the tangent because we want the tangent to be all by itself, so I'm still going to square root it. When I do that, I end up with tangent of x equals positive or negative square root of 1 over 3, which we simplified positive or negative square root of 1 over 3 in the last problem that we know is positive or negative root 3 over 3. I'm going to delete this so we can use our unit circle. So now we need to find somewhere on our unit circle where tangent is positive or negative root 3 over 3. Sine and cosine are nice because we're just literally looking at either the x or the y coordinate, but tangent we have to physically divide in order to normally find our tangents, right? We know that tangent is our y value divided by our x value. So in order for us to figure out where tangent equals root 3 over 3, we have to do a little bit of guessing and checking. But we can think about it logically. We can say, okay, well, it's definitely not going to be this point, because if I do 0 divided by 1, I'm not getting root 3 over 3, right? If I do root 2 over 2 divided by root 2 over 2, I'm not going to end up with a root 3 in it. It's got to either be my pi over 6's or my pi over 3's, because those are the points that have a root 3 in their coordinate. Are you okay with how I made that decision? I need a root 3 in my answer. I've got to have a root 3 in the coordinates I'm dividing in order to get there. So now I'm just going to basically pick one and check. You want to try pi over 6 or pi over 3 first? Pi over 3?
Yeah.
Cool. All right, so let's take pi over 3. So if I'm finding the tangent of pi over 3, I want my y value, which is root 3 over 2, over my x value, which is 1/2, right? So then I simplify. I've got keep my first fraction, change my sign to multiplication, flip my second fraction. I can cross simplify, and I just get root 3. Is that what I wanted? No, I wanted root 3 over 3, right? So if I wanted to double check myself and make sure that pi over 6 was the correct answer, I could. If I'm finding the tangent of pi over 6, it's my y value, 1/2, over my x value, which is root 3 over 2. So I keep the first fraction, change the sign, I flip the second fraction, cross simplify, I get 1 over root 3. I rationalize it, so I get root 3 over 3. Yay, that's what I wanted, right? So that tells me that if I'm looking at pi over 6, the tangent of pi over 6 is root 3 over 3. Now, I want all the positive options and I want all the negative options, so I'm going to take every single radian value that has a denominator of 6 off of the unit circle. Because all that's going to happen here is when I look at 5 pi over 6, I have the same coordinates. My x value is just negative, so when I find the tangent of 5 pi over 6, I'm getting negative root 3 over 3, which is still a possible answer. When I find the tangent of 7 pi over 6, they're both negative, so it's going to become a positive. When I find the tangent of 11 pi over 6, the y value is negative, so that's going to be my negative. So my answers here, x equals pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6.